Good morning, good afternoon, good evening, good night to everyone. Thanks for joining us. You're welcome to the CRM camp in nonlinear analysis. This week, we have the pleasure of having Antoine Zurek from Vienna, Technische Universität Vienna. So Antoine defended his PhD thesis in September 2019 at the University of Lille under the supervision of Claire Chenet-Hilleret and Benoît Merlet. And afterward, so that is since October 2019, he's been a postdoctoral researcher in applied mathematics at Technische Universität Wien in the group of Ansgar Jungel. And so right now he's in France, but he told me that he would be moving next week to Vienna, where we could hopefully have access to his office. Lucky him. And Antoine is mainly interested in the development and the analysis of finite volume schemes, preserving the structure of models of PDEs, for instance, gradient flow structure, entropy structure, etc. And today he'll be talking about some recent work he's been doing with Maxime Reden on computer-assisted proofs for the diffusion model, coupled model. Diffusion Poisson Coupled Model. Sorry about that. So please, Antoine, the floor is all yours.
Okay, so hi everybody. So I would first like to thank the organizers of the seminar for the invitation today, and I want to also thank Jean-Philippe for the nice introduction. So today I want to speak about joint work with Maxime Reden and Claire Chenet-Hilleret about the existence of some kind of traveling wave solution for the diffusion Poisson coupled model, so DPCM. And in order to prove the existence of such traveling wave solution, we use a computer-assisted proof. Okay, so first of all, I would like to explain what is the DPCM, what are the motivation behind the introduction of this model, also explain the equation and so on, and the, let's say, physical context of the mechanism described in this by this model. Okay, so the motivation behind the introduction of the DPCM was the storage of nuclear waste in France. So one option in France, which is under study in order to store the nuclear waste, is to put those nuclear waste in some steel canister, cylindrical steel canister, and then to place those steel canister in a microtunnel, so done in a geological layer, and in particular in some claystone formation. So you place those, the idea is to place those cylindrical steel canister beneath the ground, at the depth of around 500 meters. We can see here the process, let's say. And then the question is to know if this option is safe or not, because we know that when we will place those steel canister in the microtunnels, then the corrosion process will deteriorate the steel canister. And then the question is to know if those this corrosion process is strong enough to release the nuclear waste in the environment before that those nuclear waste become, let's say, harmless. Okay, or not. So we know that at some point in the future, those nuclear waste will become harmless. And then again, the question is to know if the corrosion, which will deteriorate the cylindrical steel canister, are strong enough in order to deteriorate the things and allows to release the nuclear waste in the environment. Okay, and of course, since those nuclear waste are really harmful for a long period of time, it's not realistic to do some experiments. Okay, so physicists was said, okay, maybe what we can do, since we understood quite well the process behind, is to just develop a mathematical model, in particular a PDE system, and then we will try to answer to the question of the safety of this repository concept. And actually, it's what they done. In particular, Christian Bataillon and his co-author introduced the diffusion Poisson coupled model in order to answer to this question of the safety. And on this slide, I would like to, before to introduce the equation of the model, I want to explain the main features of this DPCM. So in this model, you have three regions. First of all, you have the solution, which is the claystone formation. the metal, which is the steel canister, and in between you have an oxide layer. And this oxide layer aims to protect the metal against the corrosion process. So here the idea is that when you will place the steel canister in the microtunnel, then the metal will be covered by a dense oxide layer, which aims again to protect this metal. And the size of the oxide layer will evolve in time following the deterioration of the metal. Okay, and then the idea of Bataillon and his co-author was to follow the evolution of some charge density inside this oxide layer. And since the length of the oxide layer is really thin compared to the metal, so the idea is that the characteristic length of the oxide layer is like 1 nanometer. They said, okay, we will develop a partial differential system which take into account the evolution of some charge densities, which are involved in the corrosion process inside the oxide layer. And since the oxide layer is really thin compared to the metal, it's enough to just consider a one-dimensional problem. Okay, so the DPCM is a 1D problem, and in this 1D problem, we will follow the evolution of let's say electrons. The evolution of the density of electrons, of ferrous cations, and of oxygen vacancies. And here the idea is that inside this oxide layer, those species can just be, are transported by some mechanism that I will describe later, but they are not created or consumed in the oxide layer. They can just be created or consumed at one of these interface between the solution and the oxide layer, or between the oxide layer and the metal here. Okay, and so the main features here for the DPCM is like, so the transport mechanism I described by drift diffusion equations on the which models the evolution of the density of P. So the density, so P is the density of ferrous cations, N is the density of electrons, and C the density of oxygen vacancies. Okay, and then the idea here is that the solution and the metal are charged, which implies the existence of an electric field inside the oxide layer. And in order to take that into account in the model, in the equations of the model, we will define a function psi, which models the evolution of the psi, the electrical potential. And then the evolution of this function will be described by a Poisson equation. Okay, and at the interfaces between the oxide layer and the metal, and the oxide layer and the solution, we will have some Fourier-Robin boundary conditions, and those Fourier-Robin boundary conditions will take into account the kinetics of the electrochemical reaction which happens at both interfaces. Okay, and finally, of course, so here we need to define, in the equation of the DPCM, some evolution equation for the evolution of the three interfaces. So X0, the outer interface between the solution and the oxide layer, and the inner interface, X1, between the oxide layer and the metal. Okay, so now this is the main features of the DPCM. Now I can enter more in the details of the definition of the equations of this system. So I recall here the unknowns of the DPCM, and first of all, in this work we considered the dimensionless version of the DPCM. So the idea is that from the initial version of the DPCM developed by some physicists, we use some scaling in order to rewrite the equation of the DPCM as a dimensionless version of the DPCM. And all the parameters that we can see here in red and on the other slide also are parameters, constant, which are coming from this scaling process. Okay, so first, concerning the evolution of the electrical potential psi, so it's a Poisson equation, okay, which coupled the evolution of psi with the evolution of the density of the ferrous cations, electrons, and oxygen vacancies. And all of the spaces as charge spaces, and here the letter like ZU denote the charge of each of these elements. Okay, you have some, let's say, quite complicated boundary condition, and here what we need to notice is that delta psi 0 pzc and delta psi 1 pzc are some given constant, and V measures the electrical potential inside the metal. Okay, so the idea is that the solution and the metal are charged, and we consider that the electrical potential inside the solution is a reference potential, and so it's why here there is no letter like, I mean, it's like V0, but we consider that V0 is 0, and then you have the other potential V, which measures the electrical potential inside the metal. Okay, so this is for the Poisson equation. Now, concerning the drift diffusion equation for the evolution of the density P, N, and C. So here you have the generic form, okay, where epsilon U is again a parameter constant which are coming from the scaling process in order to rewrite the equation of the model under a dimensionless form. And so, as I said, so U is solution to a drift diffusion equation. So here you have the definition of the flux, and you have, so in this flux you describe the transport mechanism implying the evolution of U. So you have like let's say Fickian diffusion, standard diffusion, and you have a convective term, and this convective term comes from the fact that inside the oxide layer there is an electric field given by the derivative in space of the function psi, where psi is the electrical potential. Okay, so last remark on this equation, so is that this is drift diffusion equation without reaction terms, because again the idea is that inside the oxide layer there is no creation or consumption of let's say, I don't know, for instance, electrons or oxygen vacancies or ferrous cations. Okay, so those species are created or consumed at the free interfaces x1 and x0, and it's why here we have so complicated boundary condition. So here, this is the Robin-Fourier boundary condition. So here the extra terms here, this term and this term, are coming from the fact that we are working on free boundary domains. Okay, and so let's say these flux are equal to some functions, R0U or R1U. And those functions are describing the kinetics of the electrochemical reaction at each interfaces. Okay, so more in the, if we look more in the detail, so the definition of the function R0U and R1U are given by this definition here. And we can see that R0, for instance, is a balance equation between what is created and what is consumed at the for instance here the outer interface. Okay, and in particular in the case where, for instance, U equal P, I give you here the definition of the function beta and gamma. So it's not useful to remember the definition of those functions. I just want to notice two things: is that there is all those parameters here, which are parameters which describe in some sense the kinetics of the electrochemical reaction. I mean, there is a lot of those parameters in the model, which is one of the main issue. And so the let's say the form of those functions are given by what physicists call Butler-Volmer law, which are empirical law, which are well known and modelize really well the kinetics again of the electrochemical reaction. And in some we can see that as the idea is that you have some it measures the probability from one species to move from one domain to the other. Okay, so it's why you have this complicated form. And what we can also notice is that psi and U are coupled also through the boundary condition here. Okay, and finally, what I need to also to introduce and to explain a bit is the evolution equation for the moving boundaries. So first of all, you have the evolution equation for X1, the inner interface between the oxide layer and the metal. And here what we can see that the evolution of X1 is directly linked with the kinetics of the electrochemical reaction at the interface X1, sorry, and it's more or less logical in the sense that depending on the creation or the consumption of oxygen vacancies, I mean, it's an oxidation reactions, and it implies that if, for instance, the metal is deteriorate, then X1 will move to the right, and the other way around, if the metal, I mean, if some moles of oxide is transformed in some mole of metal, then X1 will move to the left. Okay, so okay, the evolution of X1 is directly linked with the kinetic of the oxidation reaction. Okay, and the other equation concerns the evolution of X1, and here there is two terms. So first of all, the idea is to, let's say, we will forget this term VD0, and we just consider the equation on X0 and X1. So it seems that, I mean, it's not, it seems, it's clear that here we link the evolution of X0 with the evolution of X1, and here there is a parameter 1 minus pi, and pi is a constant. It's what we call the Peeling-Bedworth ratio, and this ratio is the molar volume of oxide divided by the molar volume of metal. Okay, and depending on, let's say, if pi is greater or smaller than 1, I mean, we are measuring if the molar volume of oxide is greater or smaller than the molar volume of metal. So, for instance, if pi is greater than 1, this means that when you transform a bit some moles of metal, then it's take more place to transform. I mean, when they are transformed, when those moles of metal are transformed into some mole of oxide, then it takes more space than what they were taken before. So if X1 is moving to the right, then, and if pi is greater than 1, we understood more or less that X0 has to move to the left. Okay, see if X1. Okay, and the idea is that if, for instance, another example is that if pi is equal 1, then it means that the molar volume is the same. So when you transform some mole of metal into some mole of oxide, it's just exactly the same volume. So which means that in this case, it's more or less logical to say that the evolution of X0 is not related with the evolution of X1. So it's just some kind of volume, molar volume consideration. Okay, and in the particular case that we consider here, we know that pi is strictly smaller than 1, which means that we expect, I mean, I don't know, but the physicists expect that X1 move to the right, and then that X0 also move to the right, okay? Due to the corrosion process again. And finally, so you have this last term here, VD0T, and here, oh, sorry, there is a typo here. It means 0 is missing, but okay. So this term is measuring the dissolution speed. So here the idea is that the solution can transform, I mean, can eat or can, I don't know, deteriorate again the oxide layer. And I mean, you have, I mean, yes, the solution can dissolute the oxide layer, and this function here measures this dissolution speed. Okay, so this is more or less everything on the equation of the DPCM. So there is a lot of equations, there is a lot of coupling, there is a lot of parameters, and of course, due to the fact that we are working on a moving boundary domain, the mathematical study of this model is really complicated. And so far, except maybe our work with Maxime Breden and Claire Chenet-Hilleret, I mean, there is no result in the literature concerning the existence of solution for this model. Okay, however, Christian Bataillon and his co-author developed and introduced in the literature a finite volume scheme in order to approximate the solution of this DPCM system and try to see, at least numerically, if what they can observe, and if the model is quite reasonable with the physics behind, and blah 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 and blah blah. And they observe numerically really, I mean, quite interesting behavior concerning the long time dynamic of the system. And in this second part of my talk, I want to explain to you what they observed, and I will also it will be also the I mean, I will explain what we obtain in this work. So what they observed numerically. So here you have a numerical simulation done by Bataillon and his co-author with their finite volume scheme. And they observe here, so the evolution of x1, here the evolution of x0, and the evolution of the density of, so here is C, so the oxygen vacancies. And what they observe is that after a transition time, the speed of the interfaces are moving at the same velocity, and then the length of the oxide layer becomes constant. And they also observe that C then admits a stationary profile, which means then C is independent of time. Okay, and they called those states some kind of pseudo-stationary states. Okay, so the interfaces are still moving, so the domain is still moving. However, since the interfaces are moving at the same velocity, is like for C, let's say, it was like everything was on a fixed space domain, more or less. So they call this kind of states pseudo-stationary states for the DPCM, are maybe more from a mathematical point of view, we call that maybe more precisely a traveling wave solution. And okay, so first question is to know, for instance, if we are able to prove the existence of such pseudo-stationary states. And actually, Claire Chenaillier and Thomas Galouet did this for a simplified model, a simplified version of the DPCM. So in this work here, they prove the existence of pseudo-stationary states for a version of the DPCM where they just consider that the equation solved by psi was like Laplacian psi equals 0. Okay, so which simplifies a bit the system, and then thanks to some fixed point argument and let's say more classical technique for they were able to prove this kind of result. However, in this work, our main objective was to prove the existence of such pseudo-stationary state, but for the full DPCM model. Okay, and in order to do so, we used a computer-assisted proof, but as I will describe later, what we use in this work, are already well-known results or method. Okay, we didn't create new results on the concerning the computer-assisted proof techniques and so on. We just apply already existing techniques, and here the originality of the work is to apply those techniques in a really complicated system, let's say. Okay. Okay, but maybe so later I will describe a bit the approach. I won't enter too much in the detail because you are all specialists about the technique that we use in this work. But before to do that, I want to describe at least mathematically what it means for a solution to be a pseudo-stationary state for the DPCM. In the sense that so far I just move my hand and I show you some pictures and I said, okay, what is a pseudo-stationary is that, but I just want to define the equation of the, let's say, stationary DPCM, okay? And I will also present what are the, let's say, main results that we obtain in this work. So in order to introduce the equation of this stationary DPCM, what we do first is that we are working with a free boundary problem. However, we are in one dimension, so we can always use a change of variable to rewrite the equation of the system on a fixed space domain. And here, by defining the length of the domain by L of t, we use the change of variable, and after let's say, some computations we obtain, we can rewrite the equation of the DPCM on the fixed space domain -1,1. And here, so in red, it's all the new terms coming from the change of variable. And so we see that U, I mean, U is still a solution to some kind of drift diffusion equation. However, here in red, you have a new convective term. And this convective term takes into account that before to use this change of variable, you were working on the moving boundary domain. Okay, and okay, here we see also that thanks to the change of variable, and since now we are on the fixed space domain, there is no extra term, I mean, in the condition on the flux. Okay, so you just obtain a condition, boundary condition on the fluxes at the point -1 and 1. I mean, of course, the equation for psi is also impacted by the change of variable, and also the equation for x1 and x0. And I rewrite the equation under here the forms here. Okay, okay. And now from that, I just want to explain the, let's say, the ansatz that we use, starting from the definition of the DPCM on a fixed space domain. On the, let's say, the stationary DPCM, okay, system. So so we rewrite the two previous equation here on x1 and L under this form here. And then what we observe on the numerical simulation is that after transition time, the length of the domain is become constant. So I will call L, small l, the constant thickness of the domain. And we also observe that the interfaces were moving at the common velocity, and I will call this velocity, common velocity delta. And finally, we observe that some stationary profiles for, let's say, C, but it's also the case for the other density. So for the other density and for the electrical potential psi. So we will forget, in other words, we will forget the dependency with respect to time for the unknown function P, N, C, and psi. Okay, and by using this ansatz, we obtain the following equation, so which define the equation of the stationary DPCM. Okay, so what is important I want you to let's say to notice, to notice is that in this new system, so I will call a solution to this stationary DPCM a pseudo-stationary state or a traveling wave solution. And here, the unknown of the stationary DPCM are given by U, equal P and C, psi, which are independent function of time, and by the velocity delta and the thickness L. Okay, and in particular, we want to prove the existence of, at least for a given set of parameters, we want to prove the existence of a solution to the stationary DPCM, but we also want to have a precise description of the solution. In particular, we are really interested by a precise description of the value of delta and L. Okay, but before to do that, before to present the main result, I just want to focus on two things. So the first thing is that there is, let's say, 2 degrees of freedom in this system. So there is a lot of parameters, but you need to define the value of V. So the here that you have here in red. So it's the potential inside the metal, and there is the pH. Okay, so the pH is the pH of the solution. So for instance, it appears here in the definition of this constant, of this value, but the pH also is involved in some definition of the parameters involved in the kinetics of the electrical of the electrochemical reaction between the solution and the oxide layer. Okay, and which means that the physicists know that for some range of pH and some range of V, they are observing some the existence of such traveling wave solution. Okay, and so they give us, I mean, the values of the parameters was gave by Christian Matter gave us the values of the parameters, because there is a lot of parameters and it's a bit complicated, but also it gave us some range of pH and V, which are consistent with the physical context that we consider here. And so in particular for a given pH and a given V, but here I present main result, but of course we can extend this kind of result for a wide range of pH and V. But let's say for pH equal this value and V equal this value, then we can prove the existence of pseudostationary states for the DPCM, stationary DPCM, and we have this really fine description of the solution, where psi bar, u bar are explicitly non-function that we obtain on our computer. And I give here, so those values are just in order to convince you that we obtain a precise description of the pseudo-stationary state. And here I just show you some profiles of psi, p, and c for those values of pH and v. But again, this kind of results is also true also for other values of pH and v. Okay. Okay, so this is typically the main results that we obtain. And now I would like to enter a bit more in the details on how we prove this kind of results. So as I said, we use a computer-assisted proof. And again, we just apply already well-known results, so I don't want to enter too much in the details. And I will just present a sketch of the approach. And we will see that for all of you, I guess, this approach is quite standard. I mean, for me, it was not standard because it was the first time I discovered this method during this work, but okay. Okay, so yes, let me a bit describe our approach. So what we want to do first is to rewrite the equation of the stationary DPCM as a zero finding problem of the form f of x equals 0. And how we do that, so there is a few steps. So the first step is to rewrite the stationary DPCM as a system of first order differential equation that we will expand the unknown function into Chebyshev series. We will plug those series expansion in the definition of the system of first order differential equation that we obtain. And then after some identification, this will give us let's say an equivalent problem. I mean, we will obtain the zero finding problem f of x equals 0, okay, which is equivalent to solve the stationary DPCM. And here the idea is that this problem is a set of infinite equations, and the equation satisfies by the Chebyshev coefficients of the unknown functions, and also by delta and L. Small delta, small L and delta. Okay, and then now we want to prove the existence of a zero of this map capital F. And in order to do so, we will introduce a finite dimensional and approximated problem that I will call Fk equals 0. And Fk will be deduced from the definition of F. And here the idea is that we will solve this finite dimensional problem using a Newton method, okay? And the solution that we will obtain, the approximate solution that we will obtain of the problem Fk equals 0, here the idea is that when k goes to infinity, then x bar will become closer and closer to x, the solution of this problem. Okay, it's more or less our approach. So maybe I will enter bit more in the details. So first of all, I want to rewrite the stationary DPCM as a system of first order differential equation. And in order to do so, we introduce new unknowns. So the currents and the electric fields E, which is the derivative in space of the function psi. And then starting from the old formulation, let's say old formulation of the stationary DPCM, we just split this equation in two, okay, by introducing the new variable, the new unknowns function E, okay, and it's what we obtain here. And we also need to modify a bit the equation concerning the boundary conditions, so the boundary equations, let's say. And here what we do is just to replace the derivative in space of the function psi by E, and we obtain this new formulation. And now, so we expand all the unknown functions, u, gu, and e. So we expand those unknown functions into Chebyshev series. We plug the Serre expansion in the new formulation in blue. And after some identification, we obtain the zero finding problem f of x equals 0. Okay. And again, it's a set of infinite equations solved by the Chebyshev coefficients of the unknown function. And what I want to notice here is that if we use the equation on the currents, here we deduce that actually the unknown function gu is only given by its first mode, and then in the sequel, what we will do is to identify a function with the sequence given by its Chebyshev coefficients, and in particular, so here the unknown vector x will be of this form, where you are here 5 sequence, I mean, given by the Chebyshev coefficient of the function psi, p, n, c, and e, and then the other value, the other unknown value are just real value. Okay, so gp, gn, gc, delta, and l. So you have 10 unknowns. Okay, and finally, how we define the, let's say, the finite dimensional problem fk equals 0, we just truncating the Chebyshev mode, so for the k and higher, and it gives us directly the definition of our problem, our approximate problem or finite dimensional problem fk equals 0. And then this problem can be solved using a Newton method. And by doing so, we obtain an approximate solution that I will call x bar of this problem, this finite dimensional problem, fk equals 0. Okay, and then now the idea is to be able to prove that nearby x bar, there exists a solution x of the problem f of f equals 0. Okay. And in order to do this thing, we'll use let's say this Newton Coleridge type of theorem, and I think that I'm not it's not the first time that you see this theorem. So here the idea is that under which condition here the theorem state under which condition the operator here t is a contraction, and since we assume that the operator a is injective, it means that f has just as a unique 0 in a closed ball center at the point x bar and of radius r, with a precise description of r. And here the operator a and a dagger are just so a dagger is just an approximation of the Jacobian of f at point x bar, and a is just an approximation of the inverse of the Jacobian. And the idea is that if we could consider a dagger as equal to the Jacobian of f at point x bar and a equal the inverse of this Jacobian, then we will deduce a strong contraction of t around x bar. However, if we do this thing, I mean, not considering the approximation, but the exact value, we will encounter some issue to obtain precise and yes, let's say accurate approximation of the bounds of the norms here, or the operator norms here. Okay, so here the idea is to define those operators as approximation of the two operators. And then by doing so, we can estimate on our computer in an accurate way the constant here, y, z0, z1, and z2. And then we just need to prove that this polynomial here, p of r, admits two non-negative roots, and then we deduce that t is a contraction. Okay, but I think it's really classical for you. So that the description of the whole approach. I just want now to not enter in the detail of how we derive those estimates. I just want to first explain to you what are the functional space that we consider and the norms, and how we define the operator a dagger and a. So first, for the functional space for nu strictly bigger than 1, we introduce the space L1 nu here. Okay, and the idea is that we will try to prove the existence of the problem f of x equals 0, where the the series given by the Chebyshev coefficient of the unknown function psi, p, psi, p, n, c, and e live in this space. And the idea here is that in this space, the Chebyshev coefficient will decrease geometrically fast towards 0, which ensure that the function, for instance, psi, is smooth, which ensure also that all the previous computation I did before are rigorous, and it's allowed to also prove that in order to solve, it's equivalent to solve the stationary DPCM or the zero finding problem f of x equals 0. Okay, so and then we define the space x nu like that, and on this space we, for some weight eta, we introduce this norm. So I will give some details later on the definition of how we choose this weights eta. But what I want to mention here is that if we don't introduce those weights, we are not able to prove the existence of a solution to the zero finding problem. So they will play a role at some point. I will explain in few slides, 3 slides, how we choose those this weight eta in this case. And so finally, the definition of the operator A and A dagger. So here I recall what we want to do, the approximation, how we want to define those operator. And here, this map is a finite dimensional projection. So here's the idea that you apply the map pi k at each component. And in order to define a dagger, for instance, we will do that in 2 steps. So first of all, for the k first mode, we say that a dagger is equal to the Jacobian of f. So here there is no approximation. However, for the tail part, let's say, we impose that a dagger is the identity. And here the idea is that if you consider the component of the map f related to psi, for instance, but it's also true for the other, for p and c, e, you have this kind of equations, okay, satisfied by the Chebyshev coefficient of psi. And here, if you derive this equation with respect to psi k, for instance, we deduce that the Jacobian of f is more or less equal to the identity. It's more or less equal because it's not true, because of the boundary condition, the component f psi 0 contains an infinite non-zero coefficients. However, after the k first column, so we cut that, we truncate, and we put 0 elsewhere. So we see this operator as the identity, but of course there is an approximation which is done. And finally, for the operator A, we split the definition in two steps. Let's say for the k first mode, we define A as a numerical computed inverse of the Jacobian of f. And here there is an approximation. We just use the command inverse on MATLAB, and we obtain this definition of ik. And for the tail part, we also import that A is equal to the identity operator. Okay, and by doing all of this, we are able more or less to prove the main results that I stated before. There is just few comments that I want to add concerning the implementation of the method. So, as I said earlier, so one of the main issues of the DPCM is the existence of a lot of parameters. There is more than 30 parameters involved in the DPCM. And one of the main issues is that some of these parameters have different orders of magnitude. And it's really an issue, for instance, in order to get an accurate approximation of the problem fk equals 0. It's a bit complicated. In particular, here the Jacobian of fk is ill condition. So it's the fact that some parameters have different orders of magnitude. It's really complicated. So there is few strategies that we use. So first of all, we manually precondition f, okay, by factoring the worst constant, let's say. And of course, it's not really it's not a very sophisticated precondition in technique, but in our case, it's enough. So we do that. And the other strategies that we use is the introduction of the weights eta in the definition of the norm of the space xi nu. So again, if here you take eta equal 1, 1, 1, 1, 1, this leads to a z1 being really larger than 1, and then there is no proof. So here the idea is that because of the different orders of, this also issue is also related to the different orders of magnitude of the parameters. So here what we do is to see the bounds on the operator norms and so on. So y, z0, z1, and z2 as function of eta, and then depending on our need, we optimize on eta, and it's give us a nice, it's give us some values of eta for which we are able to do the proof. Okay, and it's why we introduce those weights in the definition of the norms, of the norm of the space x nu. And as I said, the existence of parameters having different orders of magnitude, one of the issues is to get an accurate approximation by using a Newton method of the problem fk equals 0. And I just want to explain to you in few words here how we compute x bar, how we can compute an accurate approximation of 0 of the map fk. And here the idea is to use the work of Claire Chenelier and Thomas Galouet. And so in this work, they prove the existence of pseudo-stationary states for the DPCM, but for the simplified model, Laplacian psi equals 0. And what we observe here with our numerical simulation is that, in fact, the approximation Laplacian psi equals 0 is not so bad. Something is happening at the boundaries, but inside the domain, psi is more or less linear. So this approximation is not so bad. So here the idea is to use their work, and in this work they also develop some finite volume scheme. And here the idea is that in order to compute x bar, first we modify a bit the definition of fk by imposing that in our case derivative in space of the function e equals 0. And then we use their work and their code, and we launch the Newton method. And then using a numerical continuation techniques, we just let's say increment the value of mu until to reach mu equal 1, and then it's allow us to obtain a really good and accurate approximation x bar of the problem fk equals 0. So that's all the more or less all the details on the implementation and the strategies that we used. To be honest, by using ideas coming from mainly Maxime, and I think I just have time to conclude and to give some perspectives of this work. So, in conclusion, so we are able to adapt a computer-assisted proof approach for the study of the DPCM, and for the first time we obtained some existence results for this model. And again, I think the originality of this work is to be able to adapt this computer-assisted proof approach for a really complicated mathematical model. And what we want to do, so the final goal of this project is to prove the existence of solution to the evolutive DPCM. However, first, we would like to study the stability or the instability of those pseudo-stationary states. So again, by just looking at the numerical simulation obtained, for instance, by Christian Bataillon and his co-author, it seems that after a transient time, then the solution to the evolutive DPCM are attract toward pseudo-stationary states, and we would like to prove the stability of for a given set of parameters for which we know that there exists a pseudo-stationary state, we would like to prove that this pseudo-stationary state is stable. So far we have some ideas. We would like, more or less to apply some standard techniques, but since we are working with the free boundary domains, we are a bit worried about some direct application of already well-known techniques and methods. So, of course, if you have a suggestion, remark of our idea, or maybe you are already maybe you tried to do this kind of apply this kind of techniques on this kind of problem, don't hesitate to tell us. And I think I will stop now. And I want to thank you for your attention. So thank you.
Very much, Antoine. Very nice.
You're welcome.
Are there any questions or comments?
Can you say something about what kinds of things you would like to prove for the evolution case?
For the evolutive case, well, I mean, we would like to prove. I mean, using the numerical simulation done by Christian Bataillon, and for a given set of parameters for which we observe the existence of a solution to the DPCM, we want to be able to prove, for instance, using a computer assisted prove the existence a long time of a solution. And the idea is to first study the stability question, and it could be a first step toward the dynamics of the evolutive DPCM.
And what does it mean for the physical problem with the nuclear waste? That there's this traveling wave, and if it's stable.
It's mean that
good news or bad news?
From what I no, I think it's more or less a good news in the sense that we see that in any case the interfaces are moving, but they are not moving too fast. So we have time, and it seems that this option is more or less safe. Depending on, I mean, I think it's safe more or less. And so this existence of pseudo-stationary states for me says that actually it's already a good step to be able to prove the existence of such traveling wave solution and the stability, in the sense that we see that the dynamic of the system, I mean, the pseudo-stationary states are reached really fast. I mean, like if you are, I mean, then the dynamic of the system is no more evolutive in some sense. So if you have a precise description and a precise understanding of those traveling wave solution, I mean, the dynamic is more or less, I mean, there is other question, but you have already it's a good step to understand the dynamic. I mean, it seems that you see after a few hours, these pseudo-stationaries are already reached. So it's more or less stable in some, I mean, not stable in the sense that, as I described here, but yes. But also the question is that can we, if those states are, if you are able to prove that those states are unstable, maybe we can ask again the question about the safety, because if at some point the interfaces are moving really fast, then we could maybe say something to the physicist. Yeah.
Thanks.
I have a question. So the choice that you made in terms of the norm. So you said that you have 10 components, and then you have 5 copies of LU1, and then you take the L1 norm of these 10 norms. Is there an advantage of taking that over the L infinity norm of each norm, say?
Yeah.
Yeah, exactly. I mean, this one. Yeah. Is there?
I don't know how to answer to. Yeah. So maybe Maxime will be a more precise answer. I mean, we tried that; it was working, and we didn't try to use L infinity norms. It's true.
But I think it doesn't change much here.
Okay.
So, like, I mean, of course, the L1 for the coefficient space, this is more or less standard. But then once you have these finitely many components, the L infinity or L1 on that is, I mean, actually for this specific system, we didn't really try, but for something similar, it's my impression that basically you shift things between y and z2, depending on L1 and L infinity, but it more or less compensates. So I don't think there is much.
So thanks to the weights, you mean that you can compensate? Yes. I mean, you change the role, but in any case, no.
But you could also have weights, the eta i's. You could also have it in the L infinity norm. But maybe maybe one more specific question to the expert. So does that imply that this choice? I mean, because you have basically 10 variables. So basically the derivative or the A has 100 components, and then you have to compute the operator norm of that. And does that choice of norm make the big operator norm computation easier?
This compared to
the max. The max between the max, you take the sum, and then after that you take some. I mean, it's a little bit. It's always kind of tedious to compute operator norms when you have these.
If you have, that's true. If you have only L1, it's always a bit simpler.
Yeah, that's what I thought, but I never used it. That's why I was wondering what are the true advantages. Is it more theoretical, or it's I
think with L infinity for the on R to the 10, let's say, we would have something similar. I would guess. I didn't try, but
okay. No, I would have to do it once because this is interesting. I've never used this. Never used such norms. I mean, we did it for Navier-Stokes, right? But when we have lots of copies like this, and I just never did it.
Yeah.
Okay.
So I think, I mean, if you, no, in some cases it makes sense to take the max, but here, I mean.
Because at the end of the day, you have kind of a little bit less control over the C0 norm of each component, right? Or you have you have a little bit less, right? Less control. So if you were to do another computer-assisted proof based on the fact that you need some C0, C1 bound on the output of that proof, then maybe you would have to work a little harder to get the information, right?
Yeah, or you take slightly more mode or slightly something better to get a slightly better bounce, right?
Sure. Okay, all right. Yeah. Okay, thank you. Other questions or comments? So I see none in the chat. Okay.
Maybe a very personal one. I was 1 hour late. I thought we're just beginning. I overlooked that in America you have changed time in the recent weeks, right?
Yeah. That's why I sent in my email. I sent my first. It was in bold. It was in bold. The comment.
Okay. So I'm sorry. I missed the talk for that reason. So for my own stupidity. Sorry for that.
Well, it will be recorded, so let's say.
Yeah, I can. Okay, I can just read it there.
Next week we move back, huh?
Yeah.
We also move, so then we're back in sync. So we have to be careful.
All right.
Yes.
Was it on purpose that we had a different hour for US last week and for Europe this week?
So last week is because the professor was from Japan, and then it was kind of very late for him already in Japan, so we made it 1 hour earlier on top of the day saving time. So yeah, I agree that in the last couple of weeks that's been a little bit confusing, but next week back to normal.
So you said everything correctly in your mail. I was the stupid one. Sorry for that.
Yeah, I tried to make it bold, but there's no way to make bold in the subject of the email, so I didn't
use capitals, right?
Use capital. You're right, JB. Yeah. Okay. Yeah. Next year, capital will be. Yes. All right. Well, welcome for those of you who just joined. So this is the end of the talk, and for those of you who missed it, well, it will be on YouTube pretty soon. Actually, all of the talks up to now are on YouTube. They have been posted. Even Jay's talk, Professor Oishi's talk, is now on the YouTube channel, so you may see all of them there. All right. So yeah.
And then if people have questions after, if they watch the thing on YouTube, maybe they can write us if they want. I mean, I don't know if it's possible or not, but
of course it's possible. Yeah, they can write you an email, right?
Yeah.
Okay. Well, that's it. So thanks a lot to everyone who showed up. Let's say that we come to an end, and next week I will be the one speaking. So I guess hopefully see you next week. All right. So thanks again a lot, Antoine. That was a great talk, and see you all next week.
Thank you for the invitation again.
Okay. Bye-bye.
Bye.